Okay, so let's move to the next step after multicollinearity. We also need to test the R-square in our test, in our regression. And again, I want to explain what is the R-square. Well, the R-square is a number that tells us how much variance of the dependent variable is explained by the model. So for example, if we have an R-square of 50.5, it means that the changes in happiness are explained by our model on 50%. So with the variables that we have in there, we can explain 50% of the changes. The other 50% we don't know. So if you think about it, in social science, it's impossible to have a model with a very high R-square because social science is psychology. We cannot understand totally the behavior of people. So it is okay, here I have it in here, to have R-squares that are low, like, I don't know, 0.05, understanding 5% of your happiness, that's quite high. And also, if you are very high in your R-square, if you have 95% or something like that, that's also a bit suspicious. So in social sciences, we are okay with not having a perfect model in terms of R-square. But in engineering or in exact sciences like statistics, physics, it's not like that, because imagine if you have a model where your model explains 70% of the behavior of air in a wing of an airplane. That's crazy, right? Imagine you have 70% chances that it's going to work. Would you go on a plane with those numbers? I don't think so, right? So you want to have 99.999%. So in engineering, it's different. In engineering, you want to have total explanation of your variable. But in social sciences, no, because it's impossible. You cannot create a model that explains 99.99% of the happiness of a population. You are a god if you can do it. So in this example, I'm continuing with the example of this happiness model. We have 0.146. It's fine. It shouldn't be extremely low, like below 1, or it shouldn't be extremely high. So it's all right. And in this case, if you have something extremely low or extremely high, I mean, you can still move on, but just report it. And it's not, you need to discuss with your supervisor, because that might be like a mistake on the data or something. But usually you won't face it. You won't face like a problem. So you usually just move on. You report, but you move on. So that's what happens with the R-square analysis. And now we're going to the last thing, because remember I told you, why don't I teach you how to interpret the coefficient and you are done? No, you need to test first the model fit, second multicollinearity, third the R-square, and if you are still surviving, then you can test the coefficient. The testing the coefficient and interpreting the coefficient is super important. It's maybe the most important thing, because it's where you will test if your hypothesis is correct or not. You will support or you will reject your hypothesis. Remember that in your hypothesis, you stated that there is a relationship between A and B, and that relationship is positive or negative. That is what we are going to do in here. We are going to check if our coefficient is significant. So that means if it is significant, that means that there is a relationship. And we are going to check the sign of that coefficient to see if it is actually negative or positive, as we set in the hypothesis. So we need to check the sign and we need to check the significance. If they are coherent with our hypothesis, we support the hypothesis. If not, we reject the hypothesis. Let me show you how it is done. So you need to check the significance in here. And basically, before you read this, because it can be a bit confusing, you need to check if the significance of your variable is below at least 0.1. If it is less than 0.1, then the significance level of this relationship is at least 90%. It is always 1 minus the significance, the level of confidence of that relationship. So for example, this is very good because we have 0.001. 1 minus 0.001 is 99.9. So we have 99.9% significance of this relationship of locus of control and happiness. So that's good. That means that there is a statistical significance between happiness and locus of control. So we are okay with testing the significance. The next thing, so there is a relationship. The hypothesis is we are doing it, we are good. The next thing is to test the sign, and you need to check here the sign if it is negative or positive. If you assume in your hypothesis that the relationship is positive, the more locus of control, the happier you are, then you confirm that in here because the sign is positive. Here you can see there are some coefficients with negative, right? But you confirm that your relationship is positive. So just with these two things, you can support your hypothesis. You expected a relationship and you are testing, you are proving there is a relationship with this at a 99% of confidence. And that relationship is positive as also stated in the hypothesis. So in this case, we can support the hypothesis. Imagine that the hypothesis, this will sound strange, but imagine that your hypothesis was that being a student will have a significant impact or it has a significant relationship with your happiness. In that case, that we will have to reject because significance is 0.73. That doesn't work, so you reject. Maybe you ask yourself, what happens if the control variables are not significant? It doesn't matter. Because that's why we call them control variables, because they only help you to improve your R-square. I told you that I will tell you why we need to add control variables. The reason is to improve the R-square. If you have a simple model, only happiness and only locus of control, your explanation power of your model is very low because you only have one variable. You need to add more things to your model to make it more powerful. But if those other variables are not significant, it doesn't matter. You only care about this locus of control. The other ones only help you to give more structure and to give more power to your model. So that's why we have control variables, but we don't have to hypothesize for every variable. You only hypothesize to what is theoretically relevant. So now you know how to interpret and how to reject or support a hypothesis in your model. But when we do research, we generally do more than one model, not only one. We usually do more than one. We sometimes add more variables, we add more controls, we add, like, for example, the logarithm of the variable. We do more models. And doing more models is called robustness test because we want to show that the results are robust, that they are kind of very powerful. That is not, we do not rely on testing our hypothesis in only one approach. We have many models. So what can happen is, because you will have more than one model, is that maybe you will, what happens if in every model you support? In every model, maybe you have 4 models, 5 models, and everything works as you expected, significant and positive, because your hypothesis says like that. If that is the case, your overall conclusion is total support to the hypothesis based on these 3, 4, 5 models. If you have the opposite, if you reject the hypothesis in every model, is total reject. If you support in almost every model, but not in all of them, we call it partial support. The opposite, almost all rejections, partial reject. And if it's just some and some, we call it mixed results. Probably you have read papers where they conclude we have mixed results, we have partial. So this is what it means, that in some models or in all models you support or you reject. So just to wrap up only the analysis part, right? Because we started with the idea of setting the hypothesis and all that. But with their analysis, this is kind of a map of how to move on. This kind of this dimension or this line is if everything works. If the reliability test works, you remember that the alpha Cronbach, that factor that we calculated, is in between 0.6 and 0.9. And only if you are doing a survey, if the reliability test works, then you do the next test, the model test. If that works, remember the model test is that it has to be less than 0.1. If it works, you move on to multicollinearity. You test for multicollinearity. Remember, it has to be BIF value less than 4. If you are right, you move to R square. You test for the R square. Remember, R square is that it has to be something in between 0.01 and 0.9. If it works, and even if it doesn't work, that's why there is no alternative, you move on. And then finally, if the significance of your coefficient is less than 0.1 and the sign of the coefficient is what you expected, you support the hypothesis. That's the ideal, that everything works. But what happens if something doesn't work in the road? If the reliability doesn't work, remember, remove questions from the database, from the database of the answers. So maybe you have 3 questions for happiness, remove one of them and see if you remove one, maybe it works. Remove it until it works. Then you do the F test. If the F test doesn't work, the model fit, you are done. You forget about that model because it's not going to work. You start from the first model, from another model. So there is no fixing here. For multicollinearity, if you have one variable that its BIF value is higher than 4, you remove that variable from your model and you will probably solve it. You do the test again and you check that nothing is more than 4. The R square, as I said, there is really no problem. I don't think you will face a problem. And if you face it, well, you discuss with your supervisor and then we'll see what happens. But instead, you can still move on. And finally, what happens if the significance of the coefficient is more than 0.1, or if the sign is not what you expect? Well, you reject the hypothesis. And then you do the next model, and then you do the next model. You keep track of your conclusions, and then you do like an overall conclusion. Total support, total reject, partial support, partial reject, mixed result. So, and that's it. That's the end of this second lecture on quantitative research. So as it's in here, we have the reliability test for surveys, descriptive statistics, the correlation analysis, and then the regression analysis as we saw it in the end with that wrap up. So I hope you understand the concepts, that you understand how to analyze and how to interpret. And when you mix this with the quantitative lab, where you will actually put it into practice in SPSS, you will have both sides. You will know how to do it, how to interpret. That's basically everything for this lecture.